Hello, here's a few more practice questions in quantum physics. Looks like we're starting with a descriptive one since this is quite short. In 1905, Einstein presented a theory to explain the photoelectric effect using the concept of quantization of radiation, proposed by Planck in 1900. Show with the aid of a suitably labelled diagram the arrangement of apparatus that could be used to demonstrate the photoelectric effect. Described how we'd use the apparatus and what would be observed. You can do different setups for this. I mean, you might want to hook up a photocell or something like that. I'm going to go gold leaf electroscope because, yeah, it's just the one that I always do. So gold leaf electroscope, we've got a zinc plate. So put that on first of all, zinc plate. Then we've got this metal zinc going down here. Then we've got our gold leaf. So we can have the gold leaf hanging down. So we've got to label all of these sort of things. So we've got the gold leaf. We've got a metal rod, well, zinc rod. Then we put all of this into an evacuated tube. So evacuated tube. So we've got all of that. Well, actually, let's put a clean zinc plate as well, because that's going to come up in the explanation. So what are we going to do with all of this? Obviously say as well that this is the gold leaf electroscope. Label each bit. Then we can say initially charge or negatively charge the zinc plate. The plate, zinc plate. So, and then that will mean that the zinc rod and the gold leaf will become negatively charged. Then we can say then that the gold leaf will move outwards, will be raised outwards, will be lifted, might be a better, lifted outwards due to electrostatic repulsion. From the zinc rod. Okay, so that settled that up. So we've got our initial setup then. Then we do the photoelectric effect part of it. So we can say then shine UV radiation on the zinc, onto the zinc plate. And what we will observe, because that's what they've got here in the question, what will be observed, we will then observe the gold leaf falling back to that zinc rod. Gold leaf falling back down to the zinc rod. Back to zinc rod. And that will mean that we've got, this is evidence of photo emission of electrons. So evidence of photo emission. So yeah, it's quite a lot you can say there, but the gold leaf the gold leaf electroscope is quite easy to describe, really. I think it's quite easy to understand what's going on. Right, part B. Describe how the photoelectric effect can be explained in terms of the physics of quantum behavior. Right, lots of things we want to list here, so I'm going to bullet point them, turn these into sentences. Right, key thing, we want a one-to-one interaction between the photons and the electrons. So that is one thing. We can then say that the energy of the photon goes to the electron, is transferred to the electron, and also that the energy of the photon is, you can either say it's proportional to the frequency or it's equal to the Planck constant multiplied by the frequency, but something like that. Something to do with a work function. So if the energy of the photon, or the energy transferred to the electron, because both of the things are the same, so if the energy transferred to the electron is greater than the work function, then we've got the electron may be released. Work function of the metal. So that's another thing, because you want to say it is of the metal. Then electron may be released, because of course some electrons need more energy than the work function. So we could then say that this leads to a threshold frequency. You might want to put that in, above which emission may occur. Emission occurs. Then you also can't do any harm by putting down the photoelectric equation. So we can do HF is equal to, so the energy of the photon, energy transferred to the electron, is equal to the work function, the minimum energy required to release the electron, plus the maximum kinetic energy that the electron can have. So we can put that on there as well. And we can also say that the instantaneous emission of electrons are emitted, or may be emitted, might be better, may be emitted instantaneously, because all we need is instantaneously, all we need is a photon arriving. So one photon can arrive immediately. So we want to flesh this one out a little bit. So I haven't got any space here to write anything down, but electrons may be emitted instantaneously because we just need one photon to arrive with sufficient energy. We don't have to wait for an energy build-up due to the arrival of a wave. So put that down there. Electrons may be emitted instantaneously because we just need a photon to arrive, and that can provide the full amount of energy instantaneously to that electron. So there's loads of things you can put in on this. Normally you're going to get maybe 4 or 5 marks. So I've put quite a lot of things here already, haven't I? I mean, this is 1, 2, 3, 4, 5, 6, 7 things there. So just pick 4 or 5 out of those 7 and everything is fine. Right, on to the next question. This question is about an experiment to measure the Planck constant using LEDs. Each LED used in the experiment emits monochromatic light. The wavelength of the emitted photons is determined during the manufacturing process. Excellent. When the PD across the LED reaches a specific minimum value, V min, the LED suddenly switches on, emitting photons of light of wavelength lambda. Okay, and they've given us the relationship here between the, well, they're asking us to explain the meaning of this equation in words. Okay, right, so we've got the, well, this is the energy of the electron. So EV min is equal to the energy of the electron passing through this potential difference. So moved through a potential difference, move through energy of the electron, move through, or maybe an electron, move through a potential difference of V min. Okay, and then we got HC over lambda. So HC over lambda equals the energy of the emitted photon. So this is a conservation of energy equation really that we've got here. You know, so joules per coulomb multiplied by coulombs, and then that is our energy of the photon on the other side. Right, part B. Describe the experiment that uses the circuit of figure 7.1 to generate the data shown in the table. The wavelength value for each LED is provided by the manufacturer. Right, so they've given us 5 LEDs with 5 known wavelengths. Okay, right, this all seems fine then, I think. So how are we actually going to conduct this? We've got our power supply. We've got this variable resistor here. So we're changing the voltage, and we've got this fly-in lead. So we can connect this fly-in lead to look at each LED one at a time. We can go through 1, 2, 3, 4, 5, and we can change the voltage using this variable resistor. Right, so that's all good. So what we're going to want to do then, let's go back to red again. So we'll start off, we'll set the voltage to 0 because we're going to want to ramp this up and see where first light is. Then we can connect the flying lead to the first LED, to LED 1. Then we're going to increase the voltage until the LED lights up. So we might want to put a blackout shield around the LED just to make it easier to see. But we'll do that until the LED lights up with a, in brackets, we might want a blackout shield. Then we are gonna, because when it lights up, this is giving us our V min. This is when we're getting the first photons coming out, so we can use this equation. This is what we're looking for here, finding that first light up point. Then we're going to repeat this and repeat an average, because that's what they've put in the table here. And then we can repeat for each LED. And we've got a whole table of stuff then. Right, okay, so there must be more for filling in the table. So on the next one, right, here we go. Complete the table. And right, complete the table, use your data, complete the graph. Okay, right, okay. Yeah, plotting things on here is always a pain. Right, anyway, complete this table then. So what are we doing? We're doing 1 over the wavelength. So, well, we'll just have the number and change it to fit. They got it on 10 to the 6 meters to the -1 there. Oh yeah, and we got the nanometers there. So yeah, we're just doing 1 over 468, and then adjust the decimal place. So 2. I've gone on to the other sheet. 2.14, and then we've got 2.43 for that one. So 2.14, 2.43, and we want to plot these. So 2.14, 2.66. So right, 2.14. Guys, this is going to be horrible to put on here. 2.14. So where's this? That's going up to 5. So 1, 4. So round about here, and then 6, 2.566. So somewhere around about there. And then the next one was 2.43. I've still got it on my calculator. What was the number? 3.02. 2.43, 3. Well, it's going to be around about there. It's fiddly to do on this screen. There's a bit of a waste of time on the video. Right, then we've got to draw the line of best fit. So we'll just go through the origin drawing up there. Okay, it's a bit wonky on here, but I'm trying to draw it on the screen. Show that the gradient is about 1.2 times 10 to the -6. All right, well, if we're using as big a triangle as possible, I'm just going to use this value up here, this last one that I put in. So what was that? 3.02, wasn't it? The V min. And then we're dividing by 2.43 times 10 to the 6, which comes out at 1.24 times 10 to the -6. So close to the 1.2. And that's our voltmeter. So that's fine. Then use the equation given in A to show that the gradient of the line is equal to HC over E. So the equation they gave us was the EV min is equal to HC over lambda. We're plotting V min against 1 over lambda. So just writing that in a different format, we've got V min is HC over E multiplied by 1 over lambda. So that is our gradient. So that is fine. We can just say, well, that is y is equal to mx in inverted commas. Calculate a value for the Planck constant using your value from the previous part for the gradient. Okay, right, so we've got the gradient, and now we just have to take this then. So our 1.24 times 10 to the -6, we have to multiply by E, 1.6 times 10 to the -19, and divide by C, 3 times 10 to the 8. And that will give us our Planck constant, because of course that is our gradient, HC over E, which is giving 6.61 times 10 to the -34. And well, we should know by now that Planck constant is joules seconds. But even if you can't on this, we've got, do our unit analysis. We've got voltmeters. Then we're multiplying by coulombs, and then we're dividing by meters per second. So the meters cancel we've got joules per coulomb multiplied by coulombs. So that's joules on the top divided by 1/2. So joules seconds. Just in case you'd forgotten what's going on with Planck constant. Right, so that's that one. One more question to do in this block. State one experiment for each case which provides evidence that electromagnetic radiation can behave like a stream of particles called photons. Right, we go photoelectric effects and waves. Young's double slit. So we'll have those. So double slit. Put Young in there as well. And then photoelectric effects. Right, B. A beam of UV light is incident on a clean metal surface. The graph of figure 7.1 shows how the maximum kinetic energy of the electrons ejected from the surface varies with the frequency of the incident light. Define the work function of the metal. Right, we've had this quite a lot, so I won't write it all out. Work function, minimum energy required to release a photoelectron from the surface of the metal. Write down the relationship between K max and F. Use it to explain why the y-intercept of the graph is equal to the work function and the gradient is equal to the Planck constant. Right, so we're going to our photoelectric equation. So we've got HF is equal to work function plus KE max. So let's get it into the format that we want for this, our y equals mx plus c. KE max, that's our y, is equal to HF minus phi. So that is our y equals mx plus c. So what were they wanting us to say? You explain the y-intercept is equal to the work function. So yeah, therefore the h is the gradient and c is equal to the work function. Okay, c or the y-intercept. So that's what they've put in the question. Cool. Use data from figure 7.1 to find the value of the Planck constant, the threshold frequency, and the work function. Okay, so h, Planck constant. So this is our gradient. Right, what have we got here? So, well, let's do it over the full length of this line. So our change in y is 40 times 10 to the minus 20. That's our change in y. Our change in x, oh good lord, right, what have we got here? So that is the 2 squares to 1, isn't it? So that's 6 1/4 of whatever units we've got. So 6.25 times 10 to the 14. Okay, so that's getting us to minus 34, which is what we want, which is coming out at 6.4 times 10 to the minus 4 joules seconds. So that's not a million miles away from our Planck constant, so that's good. Threshold frequency is then, right, so yeah, that's 5, 6, 7, 8 3/4. So it's just where we're crossing the x-axis here. Just hard to read it off the screen. So 8.75 times 10 to the 14 hertz. That's where our KE max is 0. And then the work function. So the work function is the Planck constant multiplied by our threshold frequency. So we're just multiplying these two numbers together, which is coming out at 5.6 times 10 to the minus 19 joules. So 19 there. Come out a bit wonky. Yeah, really easy calculations at the end. But yeah, nice set of questions there, because we had some good description that we had to do. We had to describe gold leaf electroscope. We had to describe photoelectric effect. We had to describe that experiment with the fly leads. So again, it's that usual split in quantum physics, easy calculations and some quite long-winded descriptions. So yeah, good practice there.